Okay, so this is a set of notes on the radius and interval of convergence for power series. A radius of convergence Okay, so the radius of convergence, if you remember, our power series has this form like I used to see some set of coefficients times x minus some a to the nth power, right? And n is going from 0 to infinity. And we said that this thing centered at a. Now, one of the things that we know is that this series will always converge at a because this reduces to 0, which means it's just 0 plus 0 plus 0 plus 0, which means it converges to 0. So I want to know how far can I get from a and still converge. So the radius of convergence is the distance x can get from the center of a power series and still converge. Now, that gets tricky because that is how far you can get from the center, but then we have a matter of the endpoints. Okay, so what we're going to do is we're going to have to test the endpoints in a different way. So we'll be able to determine the radius of convergence fairly simply, but then I want to test those endpoints, and I ultimately want to come up with what is called the interval of convergence. Which is the specific values for x that a power series converges on. Okay, so the key to this whole thing is going to be using the ratio test. The ratio test will give us the radius of convergence. Once I have the radius of convergence, I can test the two endpoints, and that will give me ultimately the interval of convergence. Okay, so this is like somewhat in the abstract here, so I'm going to use an example to kind of get at what really is happening here. Okay, so we're going to consider the series from n equals 1 to infinity of x minus 3 to the n over n. Now, this is a power series. I'll note that it's n equals 1 and not n equals 0. The reason why we have to do that is because the coefficients are defined by having an n in the denominator. So the first term, the c sub 0 term, is just 0 here. So that's not really a big deal. So this series, because this is like something, this thing is technically like n equals 1 to infinity of 1 over n times x minus 3 to the n. There, it looks more like a power series. This series, the a term is the 3, so this thing is centered at 3. Okay, so we want to find the radius of convergence. So let's play with the ratio test here. So I take the limit as n approaches infinity of the absolute value, and then we take this thing with n plus 1, so that's x minus 3 to the n plus 1 over n plus 1. And then we multiply by its reciprocal at n, so that's going to be n times x minus 3 to the nth power, right? So we do a little bit of manipulation here. That's going to give me the limit as n approaches infinity. Let's see, we can take this n and this n plus 1 and put those together. And then if I have n plus 1 x minus 3 is divided by n of them, that's just going to be x minus 3. Okay, so if I take the limit, there's no n in here, there's only an n here. If I take the limit as n goes to infinity of that, that's just going to give me 1. So this thing is just x minus 3. So I want to know so this thing I know converges when the absolute value of x minus 3 is less than 1. Okay, so this means that in this case, my radius of convergence is 1. I know that without checking any endpoints, this will converge when negative 1 is less than x minus 3 is less than 1. That's the same as saying that 2 is less than x is less than 4. So if you think about this, right, we have convergence centered at 3 with a radius of 1. If I go 1 to the left of 3, I'm at 2. If I go 1 to the right of 3, I'm at 4. So I know that I'm converging on this open interval. Now the question is does it converge at 2? And does it converge in 4? See, I know that if this gets greater than 1, I'm diverging. So beyond 2 and beyond 4, this thing is going to diverge. But it could not converge. It might converge at 2 and 4, because remember, the ratio test is inconclusive when this thing is equal to 1. And this thing would be equal to 1 at 2 and 4. So we have to check those endpoints individually. Okay, so we're going to first check when x is 2. So our power series here is going to be the series from n equals 1 to infinity of now x is 2 minus 3 to the n over n. Well, a little bit of arithmetic manipulation here. That gives me negative 1 to the n over n. That's the alternating harmonic. Yep, I can do letters today. Harmonic. This thing converges. Okay, so we're converging at 2. Okay, so let's check 4, right? So we have to check x equals 4, right? So this is the series from n equals 1 to infinity of 4 minus 3 to the n over n. That's the series from n equals 1 to infinity of 1 to the n over n. That's 1 over n. That's the harmonic. That one is going to diverge. Okay, so this means that 2 is in the interval of convergence, but 4 is not. So this is the values for x over which this series will converge. This is what we call the interval of convergence. So once we have the series, we need to know where does it in fact converge. All right, so let's take a look at a second example and see if that makes more sense. Okay, so for our second example here, we're going to use n equals 0 to infinity, so this time we can get the 0th term of n times x plus 2 to the nth over 3 to the n plus 1. Okay, so note, this thing is centered at x equals negative 2. Okay, because this should be x minus 2, that's going to make it x plus, so that's what we've got going on there. Negative and negative is going to make it positive. So let's start playing around with the ratio test. I take the limit as n approaches infinity, so I need an n plus 1 there, x plus 2 to the n plus 1 over 3 to the n plus 1 is n plus 2 times 3 to the n plus 1 over n, x plus 2 to the n. All right, so let's simplify a bit here. Okay, so taking the n's and bringing those all together, that's going to give me n plus 1 over n. Let's see, we take the 3's and we bring those together. I've got one more in the bottom than I do in the top, so that's going to be a third. And I got one more of these in the top than the bottom, so that's x plus 2. Okay, if I take that limit, this thing's going to 1. So this thing is 1/3 x plus 2. So I need 1/3 x plus 2 to be less than 1, which means that the absolute value of x plus 2 is less than 3. Right there, that's my radius of convergence. Like if I solve this inequality, I'm going to be stuck with -2 in the middle. I'm going to go 3 to the left, which is going to put me at -5. I'm going to go 3 to the right. That's going to put me at -1. You can see that, or at +1. We're going to see that play out right here. So it's going to be -3 is less than x plus 2 is less than 3. Add the 2 to everything, or subtract 2 from everything, so it's -5 is less than x is less than 1. So I'm guaranteed convergence on that. But now I got to check the endpoints. I have to check the -5 and I got to check the 1 to get the interval of convergence. All right, so let's see what happens there. All right, so let's check when x is -5, right? So that's the sum from n equals 0 to infinity of n times -5 plus 2 to the n over 3 to the n plus 1. This is the same as n equals 0 to infinity of -3 to the n times n over 3 to the n plus 1. Well, let's see. If I do a little bit of working here, if I take n of these, right? So let's just kind of think through what's happening here. I have the sum n equals 0 to infinity. That's going to give me -1 to the n, right? Times n over, and I get one of these left, so that's going to be n over 3. All right, so let's look at this. If I take the non-alternating part of this, this definitely does not go to 0. So this thing is going to fail the divergence test, because this thing is definitely, if this is a sub n, it is not going to 0. Okay, so let's check x is equal to 1 on the other end, right? So if I check x equals 1, I get n equals 0 to infinity, n times 1 plus 2 to the n over 3 to the n plus 1, right? So this is going to give me n equals 0 to infinity, 3 to the n times n over 3 to the n plus 1. There's some cancellations here, going to leave me with n equals 0 to infinity of n over 3. That again, that value is not going to 0, that's going off to infinity. So this also fails to converge by the divergence test. So ultimately, my interval of convergence will not have -5 or 1. It has neither of them. So there is my interval of convergence. All right, so there's a couple of examples of finding interval of convergence and radius of convergence using the ratio test and a power series.